Okay, so let's get started. How about that? Is that enough light? We're keeping the lights off to keep the temperature down a half a degree. Okay.
And then the one above us is like
I put just the one in the middle light on. Okay, so the syllabus quiz is not about details of the syllabus. It's just one question, kind of a reflective question. Do you want it to count or not?
I'm scared.
Don't want it to count.
Can we answer the question and then decide?
Yeah, and decide. It won't count. Okay. So anyway, here's again. This is the details. Office hours after class Tuesday or same time Monday and Wednesday, right across the hall. So let's talk about the course description. So this course is called Technology and Mathematical Visualization. However, it is really a course for people who want to gain insight into mathematical thinking, learn how to make a quest for insight your way of learning mathematics, and then help mathematical learners gain insight into mathematics and learning. Okay? So notice that it doesn't, in those 3 bullet points, it doesn't say anything about technology and visualization. You notice that?
Mm-hmm.
So what does technology and visualization have to do with that? So why is if this is what the course is about, and the course is called Technology and Visualization, why does there seem to be a disconnect, but there really isn't?
Because we're using technology and mathematical visualization to gain insight.
Okay. Yeah, that's so what is our goal of the technology and visualization? Yeah, you don't have. Okay, so here's the quiz. What percent of this course, based on these 3 bullet points, think to yourself, what percent of this course is about you in this class? Is about you in this class. So just think to yourself, based on this bullet point description, what would you say, what percent of this course is about you? Got an answer? Now, what percent of the course is about your future students? Think to yourself. Based on this 3 bullet description of the course. What percent of the course is about you, and what percent of the course is about your future students? Okay, got your answers? So what do you think? What percent of the course is about you as students in this class, MTE 250? What'd you say? Is it Chris?
Yes. You spend a lot of time from what I read, and like I say, about 40% on the actual, on myself, and then about 60% because I was reading how it's about your overall attitude and how you convey it to your students. You know, if you have a sense of it, then you can teach it back to your students. So.
Okay, so I was just asking about the first question. What percent do you think this is about you as MTE 250 students? So you said 40%?
Mm-hmm.
Okay, what other answers? What do you think? Yeah.
Well, mine might not really make perfect mathematical sense, but I was thinking it's like 100% about us because we're going to pass it on to our students.
No, but I'm asking about you. How much is it about you? So the second question is about your students, future students.
No, that is about us.
That's what I'm saying. Like, we have to learn it
Okay.
and be a part of it in order to pass it on eventually to our students. So it's 100% for both us and our students, which is why I said mathematically.
Okay. So yeah. So it's not 2/3, 1/3. It's not two. That's kind of the idea here. You might say it was 2/3 about you, and that would be valid. Or if you want to say 100% about you, but the first 2 are kind of about you. And so then the real question is then what percent of this is about your students? 100%. 100%. So yeah, you had the idea, right? 100%. because what, your values, your attitudes, as Chris was talking about, your values, your attitudes, what you believe, that's what you're passing on to your students, right? So the way that you think about mathematics, the way that you see it, the way that you approach it is what you're going to impart to your students. And so if we want our students to have insight into mathematical thinking, and if you've started the article, reading the article and working on your assignment, if you want your students to have a conceptual orientation rather than a calculational orientation, you'd better have a rock solid conceptual orientation yourself. Then that needs to be the place from which you're teaching. Okay? All right, so technology can play a vital role in all three quests. You can create visualizations to provide talking points for your own thinking and for discussions with students. Okay, you can clarify. So that was what we did on last Thursday. Okay, so it's this animation or this visual is something around which you as an instructor, you construct a conversation. You have a journey that you want to take your students on, and that's an interactive journey, right? You're interacting with the teachers, interacting with the students are interacting with each other, and everyone's interacting with the animation, and that's a structured kind of quest to understand something, all right? And that's what we call a didactic object. Okay? Another role that this technology can play is you can clarify your own thinking as you design visualizations to convey your thinking. So there's something that happens when you're making a visual, when you're actually making a visual, and you want it to look a certain way, and the great thing about this graphing calculator program is that it just displays the mathematics that you give it. So if you have a visual in mind and you're trying to figure out how I'm going to get it to look a certain way, well, that requires that you understand the mathematics and enter that in correctly. It's not about computer programming. It's truly about having the mathematics to create those visuals. And so as I have worked with graphing calculator maybe 6 or 7 years now, the first things I built to teach with were pretty primitive, but then as time went on and I really dug into it, my animations and visualizations got more and more sophisticated as I kept practicing with it. And that was a process of, always wanting to push the envelope and do more. And so that took me clarifying my own thinking as I designed them. Okay? And then you can give assignments to your students to create visualizations, right? And so they're going through that same process of trying to figure out how is it that I'm going to get this to look the way it needs to look? What is the mathematics behind this visualization? And so there's a wonderful thing that happens when you're creating these visualizations just for yourself, even before you use them with your students. Okay. So in this course, these are a few bullet points of what we'll do. A big part of that is number 2, the graphic software for investigating mathematics. We'll have a little bit, graphing calculator will be most of the course. We'll also, toward the end of the course, do a little bit with GeoGebra. Some of you might be familiar with that. So why the big deal about technology enhancing your mathematical insight? Okay, so this is what we talked about. Your mathematical understandings are a major determinant of your students' understandings, and your attitude is a major determinant of your students' attitude. Okay, so how do we do? I didn't get any emails with difficulty downloading the software. Everyone able to do it? Hopefully, I meant to remind you to bring your laptop today. Hopefully lots of you brought a laptop with it on there. Enough to share at least. Questions about the course in general? The rest is not. Any questions about the syllabus? Okay, so let's, and just to remind you, I am videoing every class. So we are rolling right now. The video is everything that's on the screen, and then the audio is just pickup of the mic from my computer, so you'll definitely hear me and most of you. There is I would add one more thing in terms of technology. We said technology can play a vital role. So the first one there is the main thing, that It's using visual as what we call a didactic object. You're going to read an article about didactic objects. What makes it didactic? It's the conversation that you have around the visual, okay? But there is another helpful thing I just want to mention about visuals. So here is this bigger here. Here's a problem situation. Everyone read it now? So Clara, the calculus cow, has been tied to a silo with a radius of 2 meters by a rope attached to the westernmost spot on the silo. The rope is just long enough for her to reach the easternmost point on the silo. Find the parametric equations for the path the cow can travel around the silo by always keeping the rope completely taut. Okay. Is the wording okay? Is it complete? Is that a complete set of instructions or description? Yeah? Yeah. The wording is fine, it's complete. How many people really get it just from reading that? Or you think you, maybe? Okay? All right, so it's worded fine, it has all the information needed. Oops. I think this is going to be too big now. Yeah, it's too big. Oh, work. What do you mean? For some reason, doesn't want to play. Okay. Try. There we go. Oh, come on. That's really sad. Well, I can do it here. I can just do manually. Here we go. I can do manually. All right. Oh, you can't see that. The silo is a little too dark there. Too light. There we go. Okay. So now, how many people really get it? Did this significantly help you understand the problem situation by seeing this, right? So now the use of this would not be what we call a didactic object. All I'm doing here is trying to illustrate or make more clear the setup of the problem to help students understanding when they get started. Okay? So that's another totally valid use of a visual, okay? Just to crystallize what that setup is saying. So this is the top view of the silo. And it said that the rope was connected where? On the westernmost point. And it's just long enough for the cow to reach the easternmost point. Got it?
Yeah, I thought we were starting over there. I was like, how's that? We're starting on the west part. Got it.
Yeah, the cow is tied to the west side. So the blue is the rope. The blue is the rope, and it's asking for the parametric equations of the path that he could take, and that's the pink. Okay. So this is the rope. This is the rope. It's attached to the westernmost point of the silo. And this is the path that Clara can take, keeping the rope completely taut always to reach the easternmost side. Okay, so let's, why don't you, let's get out, let's start playing with this. So get out your laptops and let's open up Graphic Calculator and start learning what this program is about. So here's what I'd say. I love if you guys want to explore and experiment and figure it out for yourself, but try to resist that a little bit, because if you start just doing that on your own, then you may miss a few little things that I'm trying to show you, okay? So I don't want to discourage you from being an exploratory learner with the software, okay? But just as we do these basic things, try to stay focused so that you learn all these little things that I'm trying to show you. Okay, so when you open up the software, you should get a window that looks like this. Can everyone see one? Maybe do a couple of you just want to find somewhere else to look over someone else's shoulder. Yeah, that's better. Okay, good. All right, so this is called a command line, okay? And so let's just do the easiest graph we could do here. Say y equals 3. So y equals 3 is telling Graphing Calculator to graph the line y equals 3. And then that should come up. You can adjust the color. This little purple box, if you double click on that purple box, some colors to choose from. Okay, and so then to start a new command line, you're going to do command return on a Mac, and I think it's control return on PC, and it gives you a new command line. So that's crucial. We got to know how to make new command lines. Okay, everyone be able to do it? All right, so let's do say x equals 2. Okay, and then, so for square, so say we don't want to do everyone's favorite parabola y equals x squared. All you have to do is do shift 2, and that automatically gives you the exponent of 2. That also works for shift 3. But any other exponent, you need the carets. Okay, so if you do just shift 2, shift 3, that's squared or cubed, but then any other exponent that you put on, you got to do what? Shift 6? Shift 6, and then your exponent. Okay? All right, so once you have the graph, you can click on a graph, and it gives you crosshairs, and then gives you whatever order pair you're at here in the upper left. And so then you can click on the crosshairs and drag them, and it gives you the current ordered pair of that point on the graph. Now, notice what happens when you reach an intersection point. It will lock on and give you a little knock. If you've got your sound on. And so when you hear that knock and it locks, then you've got your coordinates of the intersection. Okay. And that also happens with roots. So down there at 0, 0, it should knock and lock onto 0, 0 because that's a root of y equals x squared, the next intercept. If you want to move the crosshairs to another graph, you've got to drag off first and then start over. So once you're on a certain graph, you'll just be stuck there until you just remove the crosshairs and then start a new one. Okay, so So let's do something more like 5x to the fourth minus 3x. You can do whatever you want. Doesn't matter. Plus 40x. So here's a polynomial. I did 5x to the fourth minus 3x squared minus 18. And so so you can leave a graphing command line up there and just turn it off with the x. So you can leave it as a command line, but just turn it off on the graph. So let's do that. Turn off our y equals 3 and x equals 2. And so I want a better view of this graph. So what would it take to see this polynomial more effectively? Zoom out. So you can zoom in and out down here. Zoom out is the kind of the small mountain. So what about this? Is this helping? I zoomed out to hundreds. So what did I really want to do?
Zoom to.
So you can reset the graph if you go to graph and do the very first thing, or command R, reset graph, gives you back those original zoom windows. So we really just wanted to zoom on, what did I want to zoom out on? Did I want to just do a square zoom out? What did I want to zoom? Just y-axis, right? I want to zoom out on the y because my x is fine, right? As far as I can see right here. But I really just want to zoom out on the y. So to do that, so if you hold down the option button, if you look down here, you see that you get left and right arrows. Well, now that's only going to zoom on the x-axis. When you hold down the command, you get up and down arrows. And so it's only going to zoom on the y-axis. So on the PC, did anyone figure out what it is on PC? Control and Shift. Control and Shift gives you the abilities to only zoom out or in on a particular axis. So I'm liking this picture a lot better of my polynomial. This is a better view for me. Is it working?
Whoa, that's cool.
Now you put a Z in there.
Yeah, see. That's what I was saying.
Well, I know I was doing this.
First of all, just click on the graph. Just click, and it'll stop it. So you need to get your Z out of there. Z.
Oh, that one's right.
Right, doesn't matter. Questions so far? Are we good?
So it doesn't keep going. How do you get to a certain point where you can just see the graph without it just continuing to suck the graph and everything with it?
So that's just about zooming correctly, like getting the right horizontal zoom and vertical zoom to show what you want. Great. So you're too far zoomed out on the x. You need to zoom in on your x-axis. Because you're showing way too much x to see your graph.
Again.
Are we good on the zooming? Understand how you can zoom each axis separately.
Using this control shift for PC.
Control or shift. If you do control, it's going to change your x, and if you hold down shift, it'll change your y.
You just look for the little, if there's a horizontal arrows.
Just check the two.
Yeah, check down here. If you've got horizontal arrows, then it's zooming in and out on your x. If you've got the vertical arrows, you're zooming in and out on your y. Okay, so let's, on the first, did I show you, so I'm going to just take this out. Didn't we do sine xy equals 0.5? Well, now that looks the way it does because of the way I'm zoomed. So I'm going to go back to graph here, reset graph.
I like the other one more.
Yeah.
Go back to that one.
And so I kind of use this example as maybe more of a negative example of a visual, just showing you something. So maybe let's actually have a conversation about this this graph. So, how is it that this graph is a representation of that equation? Let's ask that question. So everyone think about that. How is it that this graph? So is this one graph or many graphs, first of all? And then how is it that what we're seeing is a representation of that equation? So maybe think about it for a second if you want to have a conversation with the person next to you. Is it one graph or many graphs, first of all? And how is what you're seeing a mathematical representation of the equation?
It's in the video. Yeah. Because the thing is, I can't make how much. That's not really, because it's not functional. It's just.
Okay, is it one graph or many graphs? It's one graph, right? This is one graph. And how is it that that one graph is a mathematical representation in a visual way of this equation? How is it?
Is it a slice of it? Or like,
It's a slice of it. It's a slice of it. Other possibilities? Zach? Tyler?
It's a collection of all points where it satisfies the function right here. So every point where sine of x times y is equal to 0.5.
So if I'm on that, so I'm going to pick that point right there. And you're telling me what now?
That if we took the x value at that point and the y value at that point and plugged it into that equation, we would get 0.5.
We would make it true. And so the graph then is what? Then what's the graph?
All the possible,
What's that?
all the possible points.
All points that if you took their coordinates would make this equation true, right? So this point right here that I'm pointing at, right there. Tell me about that point in relation to that equation. What's that? Yeah, where I'm pointing at with the mouse.
Well, if you were to take the x and the y from that point,
Yep.
it wouldn't equal 0.5.
What wouldn't equal 0.5?
So that point, it doesn't exist in that formula.
Okay. But what wouldn't equal 0.5? So you said you take this
The
point.
value you're gonna get.
the sine of x and y does not equal
Well,
0.5.
yeah.
Yeah, this is right. Yeah. So the sine, so whatever x and y values here, you take the sine of x times y, it's not 0.5. Any point on the graph?
Well,
Right, those coordinates, the sine of the product of those coordinates would be 0.5. Okay, so then I think what I showed you was z equals sine of xy. So now, y or x is the skew or the signal to graphing calculator that you want to make a graph. Because we're going to see later in class that we can use all kinds of letters to just do mathematics. All right, but x and y specifically are the cue that it's gonna make a graph. Similar to z. If you have a z, as she found in her command line, there was a z in her command line. As soon as you do z, you're cueing graphing calculator to say, do a three-dimensional graph.
oh. That's so cool.
Okay, so I'm going to turn off.
Some nerdy math.
Let me just show you a few document settings for a moment here. So if you go to graphing calculator, go to File. If you go to File and there's some adjustments that you'll want in document settings. For instance, I want to make these command lines have a bigger font. So I'm going to come here instead of 20 so you guys can see. I'm going to make it 28. And then your background. So if you want, you can make the equations make the graph to the right so that the equations will be in a column to the left. So I changed both those things. So now I've got bigger font size on my command lines, and instead of having the graph below all the command lines, the graph's to the right of all command lines. Okay, so you can just stop that by clicking on the axis, and then you can try to drag it and position it by clicking and sweeping the mouse to try to put it how you'd want it. For three-dimensional graphs, it actually gives you here in the lower right-hand corner of the wherever your command lines are, the lower right-hand corner, you can actually set the X, Y, and Z range just by clicking on there and changing those. Or you can use the zoom in and zoom out.
Sorry, how did you move the like commands to the left side rather than?
Okay, File, Document Setting, Show Graph to the right. So you can show graph to the right or below equations. And I found as I've made lots of these graph calculator files, sometimes I want them below and sometimes I want it to the right. It's like there's not, it depends on what you're doing. It really depends on what you're doing. Okay, so you could do black background. Don't recommend it with this overhead projection. Gray. Room. So room gives us like a kind of a 3D grid effect. Anyway, I'm gonna go with white. So now if you zoom, you can zoom in and out here. So this is just showing now -1 to 1 for all quantities. This is showing -0.5 to 0.5 for all quantities. Zooming out, get to see this is showing -4 to 4 for all quantities. Like I said, you can change those manually, or you can use the zoom out and zoom in button. You can also change the size of a 3D graph with, if you hit Control Z, and then click on the mouse pad and then scroll up or down the axis, it changes the size so you can get it to fill your window. Did that work? Everyone able to do that?
No, it disappears on.
Well, actually, you're on. When you push enter again, you're on the PC, right?
Yeah.
So the control command is going to do different.
What's
So
that?
maybe it's Shift Z.
Anyone on a PC figure out how to do that?
Gotta hit enter.
Yeah, so in Control Z, same thing. Enter diffusion, just push enter and over here.
Oh, hit enter. Oh yeah, and then some of you discovered there's some really cool ways to kind of colorize those. And you get a lot more choices than you do in the two-dimensional graphs. So there's some ways of shading with multiple colors or stripes or whatever's useful in the situation. Okay, so in terms of the keyboard shortcuts and functionality of it, I'm not going to have time to go over every single thing, so let me just point you to some resources. If you go to the Help menu, so graphing variables, very first one there, graphing variables in the Help menu, is helpful for symbols, how to type them in, and what their value is. Graphing variables, special names, coordinate systems. Okay, so this is everything that has to do with graphing, okay? Another very helpful, that's the Help menu. Once again, that was the Help menu, graphing variables. Another really helpful one is at the bottom of the list, keyboard shortcuts. This has tons of really important things. And so you'll come to a situation, you want to do something, and you're not sure how to enter that or what to push, on your computer to get it to do what you want to do. So look in this menu too.
What's Wolf Lacey in the
Laplacian,
Yeah, that one.
Laplace transforms.
Oh,
That's
that
from
makes
different Q.
Yeah. Didn't have to say that yet.
So, and then here's like this command plus option Z. Or let's see. So anyway, so here's some shortcuts for graphs, for viewing graphs. You can read through this. But those are really good resources in the help menu. Graphing variables, keyboard shortcuts. I also posted in the homework area, maybe I'll post it in its own place. Let's see if I can find that. So right now it's in homework, but I'm going to I'll probably make a new menu item over here. But there's this, we've started a kind of a shortcuts list for calculus, so I'm just going to put that on there as well. Command for Mac and for PC. So maybe we can keep adding to that list. As you discover things that are really helpful that aren't on that list, please email me and I'll keep improving that list, okay? So I will make a new menu item that's just for that document. Okay, over here it'll say like GC shortcuts or something like that. Okay, so that's a little bit about graphing. So let's look at GC as a calculator. So we can just open a new window maybe. So don't save, and then do new. So it does, including with all the graphing, it does everything that a normal calculator can do. And I think the format is really nice, so it does it a lot better. So for instance, you can put in 5 plus 8, and you don't even have to enter. It will just, whatever the current expression that you have typed in, it tells you what it equals. Okay? Then you can, like, for instance, just highlight the whole thing and just do Shift 9 for parentheses, and it puts it around the whole thing. Put your cursor on the outside, divide, and then to get pi, do pi, and the pi symbol comes up if you just do pi.
Do you have to go more than 3 decimals?
Yes. So that's in the document settings. In document settings, you can choose your precision. Here.
Okay.
Okay, so you can get as complicated as you want. The nice thing is it's giving you a nice image of it, with fraction bars vertically instead of horizontally, so you can see exactly what you put in. Okay, and then as you edit that, whenever you stop at a place where it's a valid value, it's giving you the value. You never have to hit equal; it just comes up. Okay, so why don't you? What I want you to do is a little practice here. So then if you want to insert text in between your command lines, you do Command T. I'm guessing it's Control T on PC. So, So what I want you to do is write an expression that computes on a command line. Write a command line. That computes So here's a little exercise. So on a command line, write an expression that computes how fast in millimeters per second the object is traveling if it's going 90 miles per hour. And now, when you build this, so don't get out your, first of all, don't do it in chunks. Don't find something and then do a new command line. You're going to do it all in one command line, one expression. Don't do it in chunks. And then also, don't use a handheld. So the whole point is that you're building this without, don't do any computations outside of just what you're typing. Okay, so you don't have to do any mental math. You don't have to do any side math, side work. You're building the expression that will give you how fast in millimeters per second something's traveling that's going 90 miles per hour. So that means in your expression you're showing every transitionary unit. Does it make sense?
Yeah.
Go for it.
How do you get from out of the text?
Just a new command line. Just the way you would do a new command line.
Oh, gotcha.
Yeah.
Okay.
So to get a new command line, same keystroke.
Okay. Control enter. There you go. Everything's so backwards.
Yeah, this has commander.
No mental math, no scratch work, just one expression that shows everything, and then gives the answer.
I'm sorry, it should be over 60. Yeah, because that'd be 1.5. Perfect. And then we divide by 60.
Parentheses are little asterisks.
That's 1 minute. So then if this is 60, so you have, this is 1 hour, 90 minutes, and then 1 hour. There's
Oh, I see what you're saying. So I'm only a minute. I need to be over second. I think it's that little over 60 seconds. It looks like calculate, you know what I mean? Yeah, I think it's that little.
But then you have to do it.
Yeah,
So
yeah. So you need another one over 60. Now you're getting the number I wasn't.
Well, I mean, the trapezoid is the
You still have the same answer.
Yeah, but you skipped a step.
You just combine.
Yeah. So now.
I don't think it's Sarah said it. Oh, okay, we have
Well,
Okay, yeah.
so I think that's the
you get it.
The point is to practice making large expressions that calculate it. So we want one expression that calculates that area. Maybe no more. So does that calculate that area? Okay. I don't know.
No, please don't ruin everything. No, it's. No, you need.
But so how did you get that?
Well, yeah, the just like this. These are different.
How did you get that?
Divide by half. But I don't know what mine is.
How did you get 12%? build the expressions and you don't have to do every calculation outside of.
This QRT.
So we're gonna take this height and divide it by height. I'm not done yet.
Okay, so build it without having done anything outside.
Okay, so how to find it?
So you put on the two. You're cheating, right? 36 squared. I'm taking a little bit of 36. Write it out. That's the right idea.
Hold that line straight to be longer.
If you're done with part B, I want you to compare your version of part A with mine and see if you think there's advantages or disadvantages to each. Okay? So make sense of what I did and compare it to yours and just see what you think. So first you got to make sense of it. So you got to dig into it and make sense of what I did, first of all. And then
Right out. Are we wrong if it's 0.5 off?
if you're what?
We have 40,233.5.
It's we have different precision probably. Your precision I've got here 4,000 what? I only have 5 digits of precision.
Oh, okay, we have 40,233.
Yeah, that's because you have more precision
Okay.
on there.
I was just confirming.
That's what I'm assuming, yeah.
So how do we do a square root?
Control V. Is that right on? We do Control V. Might be Command V. Shift Control V. It's definitely Control Command V. No, that's paste. Option V. Option V on there. Option V on Mac. Anyone got a square root on PC? I forgot what it was.
So for us, it was option.
Control Shift S maybe?
No, that's summation. Yeah, it's Control Shift R.
Go in the math. What is it?
Control Shift R.
R.
Control Shift.
Control Shift R. Thank you.
Yeah, so that's the area of control. Fire square radiation be 7.5.
It's something no, it's
Fire square.
you put one extra D. You put an extra D. The cream chocolate. So you
Control Shift.
Just in case.
Okay, questions? Difficulties? Just control left parentheses. Just highlight and then just do, sorry, shift. You just highlight what you want and then just shift left parentheses and it does it. Questions? Issues? Oh, try. I think you get one undo. You don't get multiple undos, but Control Z maybe. You just get one. Yeah, the last thing that was this morning. Sorry. Question? Question?
Control Z.
Who's ready for more work? Who's ready for more work? Listen to the tables. Asking for it. So,
Well, actually, you're just like this.
I feel like they can just type it all
Yeah.
in. We were trying to get, is it like,
You already know it's 36.
see, you know, see where it is. Okay, so that's the one about.
Yeah, that was later.
Maybe it's not maybe it's that's like one. It's hard to
that's
select things.
let's set this 100. If you have questions about these two exercises, please make sure that you can enter expressions like this. You figured out how to get expressions like this. Anybody have a question about entering these more complicated expressions?
Take some time to get used to it.
What's nice is you have computer functionality, copy and paste. You could copy part of this, start a new command line, paste it into a new command line. You can cut, all that stuff, right? You can come in here and just change one number and it automatically gives you the new result without even, okay? So what happens is as you force yourself to use this, then this is all you'll want to use. You'll never reach for a handheld again. You'll always want to use this because it's so convenient, okay? All right, so let's, page 1. Okay, so page 1, this is the formula. You're not typing that formula in for the payment given an interest rate of R, an initial amount of the loan of capital P. This is the formula. So all we're going to do is, do you see that example graphing calculator window there in the middle? That's what your computer should look like. You're forming an expression like this of numerical values to calculate payments for different interest rates, initial values, and number of months to finish. Oh, I'm sorry. Finish the table. Does it make sense? You're not entering the formula in the graphing calculator.
Come on.
What you're doing is that it should on your screen it should look like what that example is in the middle of the page. Then all I have to do is change the numbers in that same equation to get the new values, and you fill in the table. Okay?
We need to keep the old stuff we're just doing.
Nope. It's just practice.
Okay. I'm like saying this thing wrong. That's right.
Questions? You're not typing formulas in. You're typing numerical expressions on page 1. So you're typing numerical expressions.
No, you have to. Anything bigger than 2.
Just do a couple on the table. So all you have to do is, you don't have to make a new command line, you just change the numbers, the existing command line, and it'll give you the new result. No formulas, sir. Just numbers. Just give them numbers like that. You're plugging the numbers in and then typing it in that way. See? Your screen should look like that.
Oh, 61. Yeah. And so when you're first. Yeah. Like I mean. No, yeah, just change the numbers.
It's pretty convenient.
Yeah.
Well, we're gonna do even better. Turn the page over. Cool. So, read with me here. Method number 2. We can put parameters and formulas in GC to do some more work for us rather than having to keep changing the numbers in the same expression. So before we do that, let's look at some values that are reserved in graphing calculators. So we've already talked about x and y. X and y are reserved for telling graphing calculator, I want a graph. I want a graph. And same as z, that will give you a 3-dimensional graph. R is reserved, this lowercase r is reserved for the radius and polar coordinates, okay, or cylindrical coordinates. Theta and phi are, the theta is the conventional theta and polar coordinates, or trig angle, right, our trig angle. And to get theta, you would just go to a command line, type in theta, and it just becomes theta. That symbol is reserved to mean this angle swept counterclockwise from the positive x-axis. Okay? Same with pi, phi. You type in phi, and you get that angle, what? Remember spherical coordinates? Tip down from z-axis, right? Remember the angle tipped down, swept down from z-axis. Other things that are reserved, lowercase t for parametric, it's a parametric variable. We will be using that. E, pi, and I, those are reserved for their typical values in math. Okay, E 2.178, etc. Pi, of course, and I square root of -1. Okay, and lowercase n is, you've seen a lot of the animations that I've been building. Well, that's making use of what's called a slider. A slider allows you to fluidly change the value of a constant. So n, lowercase n is like a built-in slider. We'll be doing lots of that, but not yet. So what I want you to do is create this screen here. So you're going to, if you want to take an unused letter and make a parameter out of it, all you have to do is type it. So type capital R equals 0.625, as it says there, and you just assign that value to capital R. Right? Same with P and capital N. Now, if you want to use a, okay, this is really important. I get this question all throughout the semester, even though we addressed it at the beginning. So everyone listen. If you want a character string, like a word, to be a single parameter, you're going to want this, okay? When we get into complicated animations, it's really helpful that, you know, to define something so that you remember what it is. So say we want to call something like, we want the word cheese to be a parameter. Here's what you do. You do, is this forward slash, which is above the carriage return, and then type in the string that you want, and then forward slash again, and the forward slashes go away, and now it recognizes this whole character string as a single parameter. Did everyone get that? I get this, like, in a week I get this repeated question. How do I make a word into a parameter? Forward slash, type the word that you want, forward slash, and so now you see the default, right now it equals 1. So let's say we want to make that equal to 4. So then you just say equals 4. And just like you said, capital P was whatever, what is capital P right now? 260,000. Just like capital P is 260,000, now this is a single variable. This character string of a single variable has the value of 4. Okay, so you can also assign a parameter, like P or cheese or whatever. You can assign it a formula, and that's what the next line is. So if we want PMT to be the name of that parameter, we're going to go forward slash, capital P, MT, forward slash, equals, and now you're gonna type in your formula using the parameters that you've defined. So there it is right there, R over 12 times P times thing. So we're actually defining a formula.
Once you put the slash on it, that makes it
So we're defining payment to be this formula right here. So notice no value comes up. Okay, why? Because this is the line that defines payment. It's defining what payment is. If you want to know what the current value of payment is, then you in a new line you just type payment. So right now R is just so the default. If you don't define a parameter, the default is 1. So right now my R equals 1, my P equals 1, and my N equals 1. So this is just plugging in 1 for all those because I didn't define them. And calculating payment and telling me that that's the value of that expression, with all those things being 1. But you are going to put in R, P, and N, and separate command lines, define what those are, their values, and payment should come out to, is there the first one done for you? It shows on the screen, what is it? 1,686? Did it work?
Yeah.
So now, instead of going into that expression and changing the numbers, all you have to do now is just change the lines that define those parameters. And then this payment will update. This line with payment will update. Does that make sense? So do that. So just do a couple lines in that table. All you have to do now is change your lines where you define R, P, and N, and then that payment will update with the new value.
Alright,